Okay, perfect. So, hello everyone. Welcome to another meeting of our reading group. Today we have another great speaker, Julian Parker from Stability AI. He's going to talk about making transformer work for audio coding. As usual, if you have any questions, feel free to put it in the chat, or you could raise your hand and we will unmute you so you could ask your questions yourself. Now, without any further ado, the stage is all yours.
Thanks, Puna, and thanks for inviting me. It's really good to be here with this group. I'm excited to share the work of myself and some colleagues that we've done recently. Um, so, yeah, first off, I just wanted to give a little bit of an intro to who I am, so you know who's talking. I've been working in research for around 15 years now. Well, sounds like a long time. That's including PhD, but yeah, that's basically academia and industry. I had a kind of weird journey to my current place in a way. So I started out as a physics student a few years ago, got into doing musical acoustics and simulating physical systems for music. From that, got into digital signal processing, and then finally, that led me into machine learning and AI. Around 2016, I guess, is when I got into that majorly. And most of my research in industry and in academia has been focused on processing or generating musical sound using DSP and latterly machine learning and AI. So I'm very much an audio guy. I haven't been necessarily a speech person in the past. So if I say anything terribly naive about speech in this talk, then please tell me in the chat and I'll learn from you as well. Yeah. So just a couple of words about where I work at the moment. So Stability AI. You may have heard of us before. So probably you've heard of Stable Diffusion, which was one of the first image generation models to make a buzz on the internet. The company's gone through kind of lots of different incarnations over the last few years, and the current one is quite exciting. So we've got a really all-star team at the head of the company now, including James Cameron of Avatar fame, who's on the board. Um, and our basic kind of goal these days is to make open weights generative models that are targeted for use inside professional media production workflows. So that's things like Hollywood, TV production, the music industry, and we do that across all the different modalities that are important in these production forms. So image, video, 3D, audio, everything. So I work as a researcher in the audio team, where we're mainly concentrated on music and general audio generation. Um, you might have come across one of our models called Stable Audio Open. That's something we released in the middle of last year. That's an open weights model for sound effects and to a certain extent music generation. Did pretty well for us. It was number one on Hugging Face for a couple of weeks. We were quite pleased with that. Yeah, you may have heard of that. So what are we talking about today? Yeah, I wanted to basically share some work that I did, I guess, around the middle of last year. The primary work was going on. We wrote that up at the end of the last year and submitted it to iClear, and it was accepted. We're going to be presenting that in Singapore in about a month, actually. So if you're there, come along and say hi. And this work was done. So the primary authors were myself, my colleague Shubo, who is now at Meta, actually, and my other colleague Anton. Um, and I thought for this talk, seeing as it's a bit of a longer slot, rather than just like replicating a conference talk and just going through the paper, which you all, of course, can read, I take a bit more of an informal approach and just talk about some of the thought processes and like the challenges that we came across whilst we were developing the techniques in this paper. So, yeah, let's set the scene first. Yeah, so like I said, this work mainly happened kind of the middle of last year. I think I actually started thinking about it in March. Yeah, it was March for sure. And basically, what was the situation at that point? Like, why did we start thinking in the directions that we were thinking in? Well, at that point, basically, all the most successful codecs for generative use, especially for music, but as far as I know, also for speech, I'd say they were broadly based on the encodec architecture. That also includes, for example, the types of networks that we were using for, well, as VAEs for music generation with diffusion. Um, and obviously, these network designs have been working really, really well. But if you look at them, they're also kind of like old, I suppose. So they're convolutional architectures. They're usually built on even maybe not even the latest kind of techniques in convolutional architectures that are used in, for example, computer vision and things like this. So, like encodec, for example, is basically like a ResNet. It uses dilated convolutions. I mean, it works, but it's old, right? So the question is, what happens? What happens if you use an architecture that isn't quite so old? I mean, the other thing is that yeah, basically because of this kind of less modern architecture, these models don't necessarily scale very well. So most of the published good models, like encodec, like DAC, um, they're based on a relatively small parameter count. So something in like the 100 million or less range. I mean, really, really big models go up to 200 million, but then you start to get the kind of typical problems of scaling convolutional models. So they're both in terms of inference speed, and in terms of just the stability of the training when you're scaling. Yeah, and also we were a little bit frustrated because most of there's lots of papers improving on these codecs, um, but basically most of them were keeping the backbone the same and then layering on more and more complicated training objectives or like extra discriminators. And we thought let's try something different and see where that takes us. So yeah, we decided we basically wanted to make a variant of this kind of model, but using transformers as like the first class architectural component. And yeah, why would we want to do this? I would split the reasons for this into kind of three. So one is the obvious reason, because let's be honest here, right? Like using transformers to try and do a particular task, that's not a novel thing in 2024 or 2025, right? And there's good reasons why you would do that. And there's good reasons why it's become the default architecture for so many problems. And that's basically the scaling properties. So you can go up to large parameter counts without having huge problems. And it's also increasingly, I would say, about the kind of the whole ecosystem of implementations and optimizations that are then built around the transformer architecture. So if you can make your model be primarily based on transformers, then you get all of these kind of side benefits from that. Another more personal reason is like I mentioned, I'm someone who's been involved quite heavily in signal processing and DSP in the past. I don't know. I've had a lot of research projects where I've been hit by the bitter lesson, I would say. So I'd come up with some really clever signal processing idea that I was sure was going to work incredibly well in a machine learning context, and you know, many times it didn't. We can't necessarily always predict what's going to work well in a like a trainable context rather than in traditional signal processing, right? So part of this work was kind of my reaction against that. I thought, you know what, let's try and remove all of the clever signal processing stuff, just make a really, really like plain basic architecture, very generic, and then see if that does well for us. And the other more kind of principal reason that we wanted to explore this kind of architectural choice is that so if you know anything about traditional compression algorithms, you'll know that they very, very heavily leverage like the non-uniform distribution of information. So like a really basic example of that is, for example, the zip algorithm, right? So with the zip algorithm, you're able to compress sections of very, very similar data, for example, like loads of zeros after each other, into just like a very, very small amount of space. So convolutional neural audio codecs, they're not really able to do this at all, right? So convolutional yeah, convolutions have a limited receptive field. They don't necessarily have an efficient way of moving information around over a long sequence. So in a way, they preserve kind of locality, even once you've come up with a compressed representation, right? So our feeling was that this would be a limitation. If you have a long period of silence and it's going into a neural audio codec, that's not going to be compressed to a very small part of the latent. Um, yeah, and our intuition was that potentially an architecture that has attention involved would be better at doing this. Obviously, attention is much, much better at moving information around over long sequences. It doesn't necessarily have the same kind of like locality bias, although obviously when you're using rope and things like this, that does introduce that a little bit again. But basically, yeah, this seemed to be like a reason why it might be interesting to explore transformers in this context. Yeah, and basically, at least as far as we understood at the time, there hadn't really been many serious attempts at using transformers in this kind of architecture at that point. Since then, there have been many attempts, I would say, some parallel with ours. I mean, who actually, I don't know who was first. So a lot, basically, I think three or four different attempts at this came out at the same time around the beginning of this year, end of last year. I think you've even had some people on in the conversational AI reading group who've been exploring different directions, right? So it was clearly an idea that was in the zeitgeist at the time. Yeah. And so what did we want to achieve on a broad level from this project? So first off, like I've mentioned now several times, we wanted a viable architecture for compression of audio, not just speech, but audio in general, where the majority of the parameters were living in transformer blocks. We wanted to target high quality reconstruction at a very low bit rate. We wanted to find some evidence that scaling parameter count would improve reconstruction quality. And then we had the kind of selfish researcher goal of we just wanted to try out some new techniques and see what would happen, right? Um, Maybe a note to frame also some of the research choices we made here. So we don't actually have production speech models at Stability. Like that's not like an end use that we're present in. Um, So yeah, this we kind of approached this in many ways as a research work, and many decisions I would say reflect this. So sometimes we chose to do the interesting new option when we could have used like an established and proven to work option. Maybe the resulting model it would have been better even if we'd gone the conventional route, but we decided for this we wanted to always choose the path of novelty for our own satisfaction and just to explore the space more fully. Yeah, so what kind of design decisions do we need to make when we're designing a codec using transformers? Um, yeah, well, first off, let's set the broad design principles we chose. Um, yeah, I guess the big one was that we decided that we didn't want to move too far away from this traditional kind of encodec and DAC neural audio codec architecture. So that's basically something that has an encoder. I mean, it's basically an autoencoder, right? So as an encoder, as a bottleneck, it has a decoder. And then usually in these models as well, because of the problems with just reconstruction loss in a autoencoder, some kind of adversarial loss is used using a discriminator. So we decided we want to stick to that paradigm. We didn't want to use a generative decoder like you would use in a diffusion autoencoder. We didn't want to use any kind of generative post filter or anything like this. We just wanted to use this plain structure, see if we could make it work with transformers. Yeah, then as I said, we wanted to eliminate the majority of convolutional elements. We wanted to use basically standard transformer blocks, so not necessarily change the architecture too much there, not use necessarily things like conformers, but basically just, plain transformer blocks like you'd use in an LLM. We wanted to target the bottleneck to be discrete and to have a very, very low number of tokens per time step. So this was something like I think at the beginning of this work we were dreaming of basically like a single token model. I'd, I'd say we did manage to achieve that in the end with caveats, but in practice we still need to use like one, two, three tokens per time step. But that was basically that was our motivation at the start. We didn't want to do like an eight level residual vector quantized bottleneck or anything like that. Yeah, and we wanted to prioritize natural kind of audio quality. So a lot of the very high compression codecs that we'd listened to at that time tended to have a more kind of, I mean, for speech, they could be pretty good in terms of intelligibility, but they might not preserve so much of the prosody or just like the emotional and natural content of the voice. And that's not what we wanted to do. So we wanted to have something that preserved, preserved the feeling in the voices. So the first big thing you've got to think about when you're designing a transformer-based codec is so as opposed to convolutional networks, in convolution, it doesn't matter if you're just starting with like a single channel of audio waveform, right? So the standard techniques of building up to a large embedding via like repeated application of strided convolution, channel expansion, things like that. In a transformer, we don't really necessarily have an option like that. So we need a way to transform our raw audio waveforms into something that has a larger channel dimension so that we can interface it more easily with the transformer blocks. And there's a bunch of options for doing that. So first off, I guess the common choice, I mean, also with convolutional networks, to be honest, common choice is to use spectrograms. Um, so we kind of rejected Mel spectrograms off the bat. They're very popular, of course, in this domain. We didn't want to be limited by basically the inversion technique that would be needed if we were reconstructing Mel spectrograms. So if you're doing Mel spectrograms, then they have the limitation that they don't include phase information and also the process of binning everything into the Mel scale is not perfectly reversible. So obviously, if you're working with Mel spectrograms, you either have to use like Griffin limb reconstruction, something like that, or you have to use a vocoder model like Hi-Fi GAN or something like that. And we didn't necessarily want to place like this hard limit on the quality that we could reach. So we rejected that out of the box. Yeah, we also decided we didn't want to work with linear complex spectrograms. That was primarily because they're not what's called critically sampled. So maybe I'll define that here in case people haven't heard of that term before. So that's basically something that's a property you talk about when you think about time frequency representations of audio. So if something is critically sampled, then it means the time frequency representation has basically the same amount of data as the original waveform, right? So um, linear complex spectrograms do not conform to this unless you basically have no overlap and no windowing, which has its own problems. So if you're doing, for example, standard spectrogram settings like a Hanning window with two times overlap, you're actually expanding your information before you try and compress it. So yeah, by two times in that case. So we thought, we don't want to do that because basically we're making the problem harder for ourselves. We're making the data bigger before we start to compress it. So let's not do that. Yeah, I mean, we also could have used basically existing convolutional up and down sampling networks, so the kind that are already used in the convolutional codecs. Um, we did in fact try that, and it works. It works reasonably well. The main reason we didn't go with this in the end is actually more about computational complexity. So um, if you look at especially the inference speed of these kinds of convolutional codecs, a lot of the time is actually spent in the last few layers that are translating, especially on the upsampling direction, doing transposed threaded convolutions that are targeting like the original audio rate. Um, in fact, most of the time is spent there. Like that's really dominating the inference time. And we didn't want that to be the case, right? So we knew that if we had this kind of interfacing with the raw audio world, that we were going to have that same kind of inference time bottleneck, and that's not what we wanted to do. Um, yeah, there is also a whole other class of time frequency representations in addition to spectrograms that kind of fit the bill for this task. So things like the modified discrete cosine transform, like wavelet filter banks, things like this. They, in general, we tried them. They work pretty well. We found in general the errors, like the reconstruction error when it was in this domain, was a bit more audible than what we chose finally. And also, again, with these kinds of representations, you usually don't have technically perfect reconstruction. It might be very, very close to the level of like, minus 60 dB, minus 50 dB or whatever, but it's still kind of like a bar, like a limit on the upper level of quality. So what we found to work best in the end, and I think some of the other works who have been exploring similar things to us, I think the TS3 codec in particular that was presented to you folks in January, I think they chose a similar thing here actually independently. So both of us discovered that actually patching works pretty well. So that basically means exactly as with an image, you just take your consecutive raw audio samples and lay them out across the channel dimension with a certain patch size. That might seem like a really naive approach, at first glance, but actually it has pretty good theoretical justification in the signal processing literature as well. So that kind of representation, it is actually a time frequency representation, and it used to be called the polyphase representation. So this is actually used, for example, in multi-rate signal processing systems. So it has like actually a theoretical basis behind it. So even though it looks like a naive solution, it's not actually it's not actually so naive. Um, and the reason we like this in the end is it's very, very simple. It basically has zero computational load associated with it. It's just a reshaping of the input tensor. And our kind of initial experiments showed that error in the patch representation tended to manifest itself mostly as things that were quite noise-like. And this perceptually seemed to be better to us. Let me just check how we're doing for time. Okay, yeah. Maybe I need to speed up a little bit. Um, yeah, so the next big choice was to decide what kind of bottleneck to use. Um, I guess this is where the desire to try new things came in a little bit. So, of course, the natural choice for this kind of model would usually be some variant of vector quantization or RVQ. Um, I mean, we kind of decided early on that we didn't really want to pursue that. Mainly because we didn't want to use lots and lots of residual tokens. I mean, also it complicates the training. You have to use additional auxiliary losses. You have to use things like straight through gradient estimation. So we decided instead to go for the FSQ approach, which was fairly newly published at the time. So for those who haven't come across this before, this is a really elegant, simple way of having a quantized bottleneck. Basically, you just have a linear mapping down to a very low number of dimensions, usually something like 6, 8, 5, like really low. And then instead of like in vector quantization, you're basically finding clusters in the vector space and assigning them numbers, right? So that's not what happens in FSQ. In FSQ, you just take each of those individual dimensions in your low dimensional representation, and then you quantize to like a fixed number of points over the interval between -1 and 1. So very, very simple. The quantization points don't move. They're not trainable. All that's trainable is basically the mapping down to that low dimensional representation and the mapping back up. And this has some nice kind of side benefits. One being that if you don't want to use straight through gradient estimation, you don't need to. So now the quantization levels are distributed evenly. You can actually emulate the quantization process using noise, which is handy. Um, Yeah, and you don't necessarily need these auxiliary losses to get the code book to behave sensibly. I mean, there's also quite a lot of work showing that FSQ in general has high code book utilization, which seemed like an attractive property as well. The downside is that so they're a little bit FSQ bottlenecks are a little bit fiddly to configure. So if you want a reasonable number of so if you want your token dictionary, essentially the number of numbers describing a single time step to be relatively small, you're limited in how you can configure the bottleneck. So you can't have too many dimensions, and you can't have too many quantization levels per dimension. Yeah, and we thought actually, I mean, we thought we could get around this. So we thought about this a little bit on the theoretical level and realized we could actually come up with a kind of residual version of FSQ that would get around this limitation to a certain degree, which I will just describe briefly here. So the way that you do this is basically, I mean, we arrived at this kind of intuitively actually by thinking about the nature of the FSQ algorithm. So if you look, so you can see in this chart here, we've listed out the quantized positions that are associated with different level numbers for a single dimension in FSQ. You can see if that you're careful about how you pick the number of levels, you actually end up with kind of each set being a subset of the ones that come after it. And you can leverage this property along with some scaling to basically take an FSQ that's been trained with, for example, 9 levels, and decompose it into a form, well, basically a residual form where you have 3 level FSQs cascaded with the later versions being scaled. This is really handy. So, like, we kind of like this result because it basically meant that we didn't have to worry about the residual part at training time at all. We can just train with a number of levels that would be impractical for the codebook size in downstream uses. But then after the fact, then split that up into multiple smaller codebooks that function basically the same way as RVQ in terms of inference. Yes. So, having thought deeply about these different points, it was time to put everything together. How did we do that? So, here's the general architecture that we arrived at. So, it's relatively simple. So, we have these patching and unpatching blocks at the input and output. We have an encoder and decoder section, as you would normally have in such an approach. The encoder and decoder are made up of a bunch of blocks that are essentially like transformers, preceded in the encoder case by a strided convolution that does a little bit of downsampling, or in the decoder case, a transposed strided convolution that does a little bit of upsampling. So you might think, so we've been trying to eliminate convolution. Why have we still got convolution in this architecture? That was basically to address a practical constraint. So if you want to do a large amount of downsampling with patching only, then you end up with really, really large embeddings going into the transformer. So a kind of rule of thumb that we found working on this, also to be honest, from working with DITs for diffusion, we found that in general you don't want to be inputting an embedding into a transformer that is much bigger than around a third of the actual internal embedding dimension of the transformer itself. I don't know. There must be a result in the literature about this somewhere. I haven't found it. If anybody knows, then please stay in the chat. In the chat, I would be really interested. But this is something that we found in practice. So that meant that, so say you've got a normal kind of transformer embedding dimension of 1024, you're limited by the patch size that you want to put into that before things will start degrading in terms of performance. So in that case, it would be around like a patching level of 300. And for us, that wasn't enough downsampling. We wanted to get to lower temporal rates. So we still had to use a little bit of strided convolution inside the architecture to provide that little bit of extra, compression essentially. And for this work, we did that just by inserting strided convolutions between the layers. Yeah, so the transformer blocks themselves are basically completely standard, apart from one thing. So they use a sliding window mask, actually a non-causal sliding window mask. So that's like instead of like a causing sliding window mask would look like a causal mask, but you're only looking, say, 100 tokens back into the past. For a non-causal one, you have that same window, but it's centered on the query point instead of just going backwards. The reason we chose this is because we were aware that we would want to run this model over variable length audio, essentially. So we needed to introduce some kind of mechanism that would stop it breaking down as soon as it saw a like a length of audio that it hadn't seen during training, and sliding window fits that bill perfectly. So yeah, having defined the architecture, we wanted to do some experiments. So we're going to choose data for this. So yeah, the final paper is actually only talking about a speech model, but in parallel to that, through most of this work, we were also working on a music and general audio model. So the speech model we picked to be using 16 kilohertz mono audio because that's the data sets we had available were in that format. For the music and general audio, we were targeting 44.1 kilohertz stereo because, again, that was the standard we were using in other works. Yeah, we kept things fairly simple. For speech, we just used Libri Lite, clean, clean audiobook recordings mainly, with very simple and safe licensing conditions. And yeah, it just seemed like a good fit for us. For the music and general audio version, we used the same data set that we've used previously for Stable Audio Open, which is Creative Commons sound effects and musical assets from Freesound, which is a website that has Creative Commons audio, and also from the Free Music Archive, which is also Creative Commons. I would say both of these data sets are quite modest in size. They're definitely not like the level that you would see for some models. They were manageable basically, and enough to do a proof of concept. So yeah, having put all of these things in place, we started training models. And of course, as you start training models, you start getting problems, right? And then you have to fix the problems. So a big one for us was we noticed that basically training would be incredibly unstable unless we were really aggressive in how we stripped silence from the training data. And that seemed like a cop out to us. So we didn't want to come up with an architecture that couldn't deal properly with silence, because a lot of audio potentially is silence. It has to be able to deal with silence gracefully. And we did a bunch of digging and trying to work out where this problem was coming from. And in the end, we arrived on it being essentially the layer norm layers in the transformer itself. So by default, these have a pretty aggressive epsilon. This is fine when you're training a language model or anything that's based on trainable embeddings because the network can adapt basically the embeddings itself to lie in the correct space. But when you're putting in something like an embedding that's basically just derived from the input data in a very, very simple way, like patched audio, this doesn't really work so much anymore. So you might have an embedding that's coming in that is almost entirely like a silent portion or like a low-level noise portion, and the layer norm is going to amplify that up to be large. And this seems to interfere with the training, or at least it did with the data sets we were using. And we found that the way of getting around this was to basically relax the epsilon in the layer norm. That means that below a certain level of kind of magnitude, the input embeddings don't get amplified anymore. They're just allowed to stay at zero. And that stopped this noise being injected into the network essentially and made things work much more smoothly. So another problem that we came across, and this is one that I want to examine in more detail in the future. So we found that yeah, moving to a really powerful transformer decoder, it revealed lots of problems with the existing losses that were being used to train this kind of model. So we found, for example, that whereas STFT losses tend to work really, really well with convolutional models, with the transformer based autoencoder, it didn't work so well. It would produce essentially periodic artifacts, so like robotic kind of repetitive qualities in especially in the upper frequencies of the reconstructed audio. I mean, there's a couple of papers actually that are examining related things. I think this is in the end potentially to do with how you do the windowing and how you choose your selection of different FFT sizes when you're doing a multi-resolution STFT loss. But yeah, the transformer decoder seemed to really latch onto these kind of weak points of this particular loss and amplify it, which was not good. So we coped with this by essentially de-emphasizing that element of the loss. So we used STFT loss weighted normally at the beginning of the training, and then we have a decay that rolls it down over time. And by this, we managed to get the benefits with getting into a good kind of region at the beginning of the training, but we don't have the problem with it locking onto these periodic artifacts late in training. Another interesting thing we discovered was that the discriminator choice seemed to introduce all kinds of interesting different artifacts that you also don't necessarily see in convolutional architectures. Usually in the form of, so again, kind of periodic things, but different to the problems we were seeing with the STFT loss. So you would have, especially in the high frequency regions, like little spots in the spectrogram or little lines, and they'd be quite disturbing when you'd listen. So you would really notice them, and it was not good. And we tried actually basically pretty much every discriminator off the shelf out there. So we tried the encodec one, the DAC one. We tried Big Vegan. We tried all kinds of stuff, and they would all have different variations of this problem. So we did a bit of digging and tried to work out why this would be the case. And I can show a couple of plots that illustrate this here. So, I mean, we need to explore this in more detail maybe in a future paper, but basically it seemed that most of these discriminator architectures had, to a certain extent, at least when they're initialized, a kind of periodic bias in their sensitivity. So the plots you're seeing here are basically So this is in a way kind of like a time frequency representation of the input, and you're seeing the derivative of a bin in that frequency representation with respect to the rating that the discriminator assigns to it. So you're kind of seeing the sensitivity of the discriminator to different elements in the input spectrum. So you can see on the left here, this is basically the pattern that you get if you take like a plain initialized encodec discriminator and examine it in this way. So it has all of these kind of horizontal and vertical lines, and they actually basically broadly line up with where we were seeing these spots in the spectrogram. So this seemed like a good candidate for what was going wrong there. Yeah, and to try and mitigate this, um, I reached back into my past research and thought about some methods from. So this idea of choosing uh, parallel things in such a way that they don't overlap in a periodic way. That's a really common problem when you're designing reverb, right? An artificial reverb. And you mitigate this problem by basically choosing your repeating thing um, to not be harmonically related to the other repeating things that you're trying to overlay. So basically, this means that you can, instead of having like, for example, FFTs at like 2048 bins, 1024, 512, 256, etc., you can space them out in a much more irregular kind of inharmonic way. And by this, you're reducing like the way that the peaks in their sensitivity uh, correspond and overlap. And you reduce this overall kind of like grid effect. So yeah, you can see basically this on the right is how this sensitivity map looked like after we had chosen this irregular spacing. So you can see there are still kind of gridded elements, but it's basically much more noise-like. And we found basically in practice that this also eliminated these spotty artifacts and you ended up with better audio quality. So great, it's a result. How are we doing for time? Okay, maybe 10 minutes left. Um, yeah, so having corrected these initial problems, we did large training runs. So we trained basically music and speech models on usually around 32 H100s for something like 500K steps, which would usually take like 5, 6 days. Um, yeah, and we got some results. So the results from the speech models were quite encouraging. So we got really good audio quality. We could hear that actually pretty early on in the training. But we had an issue where basically rare phonemes in the speech would be dropped or slurred. Sounded quite disturbing, actually. It's almost like because the combination of the naturalness and the slurring gave a very uncanny quality. Anyway, it's not something that we wanted in there, obviously. We need accurate reproduction of the speech. So we actually fixed this by taking our pre-trained model and then fine-tuning it further with like an additional loss on the eventual decoded output of the speech basically using the WAV-LM model. So we took that off the shelf and then we use that to do a perceptual loss. So we take the output audio, we feed it into the WAV-LM model, we take embeddings from various different layers instead of inside WAV-LM, and then we basically calculate a distance between the real and the reconstructed audio. So the idea there is that we end up with something that's like a reconstruction loss, but it's more biased towards the bits of the audio that are important for intelligibility. And this actually worked super well. So this boosted, for example, a lot of our spectral metrics massively, and it eliminated the intelligibility problems that we had before. And that's basically what gets you to the results that we showed in the end. So at this point also, yeah, like so we had our first music models. So at this point, basically we dropped that line of research for this particular paper, at least. Obviously, I'm a music guy, so I there's going to be something more coming in that domain in the future. But for this paper, we had to drop it. So the musical version of the model was basically having similar issues. So what does an intelligibility problem sound like when you're thinking about music or general audio instead of speech? Well, I think in our case, it basically sounded like the model being too generative and being too free with the outputs. So you would get music that came out of the autoencoder that sounded similar, had the same vibe, but you'd have an instrument was slightly changed, or like a hi-hat would disappear, or like something would have a slightly different timbre. So for us, this wasn't like fulfilling the goals. So basically, at that point, we thought, okay, we're going to have to drop this. We'll leave that for future work, and that's primarily because we didn't have. So this WAV-LM fine tuning that we could do for speech, we didn't have an equivalent that we could do for music. So something like WAV-LM or Hubert doesn't exist in the same way for music. There's a couple of models, but yeah, they're not as mature, they're not as developed, they're not as successful. So we couldn't take that approach for music, so we had to drop it. Yeah, I'm going to go through the evaluation results a bit quicker, I think, because you guys can look at the big tables in the paper. Like it doesn't really add much me talking about this, right? But basically, the result of this research was a pretty good model, I would say. So, yeah, if you evaluate it by objective metrics against other codecs at similar but usually greater bits per second, whereby the majority of objective metrics performing better. So the closest in general was Mimi, which makes sense. That was essentially concurrent work with what we were doing. That came out basically 2 weeks before we finished this paper. Does pretty well as well. But we seem to do pretty well in terms of like the naturalness. Like, yeah, the reconstruction sounded good, and this was reflected in the objective metrics. We also saw this when we did subjective tests. So we did a Mushra test with a bunch of participants gathered both from like researchers that we know. I also posted it on LinkedIn, and we gathered a bunch of people basically. They did a pretty typical Mushra test between our model, Mimi, and then a bunch of other baselines. So it differs a little bit from normal Mushra in that we didn't include a hidden anchor because that seemed to be the standard for other evaluations in the field. Um, and yeah, we were super pleased by these results. It seemed like in general there was a very clear preference for our model. It's very, very close to the ground truth. So you can see this reflected in the graph here. And I'd say it was actually the preference was kind of maybe a little bit bigger than we would have expected from the objective results. And I would attribute that to, I mean, the decisions we made seem to have prioritized the naturalness of the audio. Um, and yeah, people seem to, this is attuned to what people like to hear, right? So it seemed to produce a more positive response. So if you want to listen to lots of examples, you can go to the website associated with this, which I believe was linked in the announcement for the talk. We can share it separately as well. But I will just play you three now so that anybody who hasn't looked at gets a little bit of an idea. So here's some ground truth audio. Let's hope that the audio sharing is working actually.
I saw at the Hamburg Museum the skeleton of one of these creatures, 30 feet in length.
Okay, so that's the ground truth audio. Here is our model at 400 bits per second.
I saw at the Hamburg Museum the skeleton of one of these creatures, 30 feet in length.
And then the kind of closest equivalent was Mimi and at 0.55 kilobits per second. And this sounds like this.
I saw at the Hamburg Museum the skeleton of one of these creatures, 30 feet in length.
So I think you can hear this distinction quite well, right? So Mimi still sounds good and it's perfectly intelligible, but it has a little bit more of that kind of like robotic voice quality. So yeah, we were pleased with that result. Right, and like I mentioned initially, our other big goal was to like establish at least informally that there's some benefit to scaling this kind of architecture. And we did this by repeating the pre-training phase without the WAV-LM loss, with versions of our model with various different parameter counts. So we did a 240 million version, 540 million version, and then the 950 million version is basically our main model. And as you might expect, the metrics scale pretty simply with the size, which was satisfying. So it's clear that in there is some benefit to scaling, and you do get some benefit from it, essentially. What's interesting actually is so we've done some work more recently, and also I think others have that have shown that this kind of architecture actually scales down quite well as well. So you can actually get pretty good results even going down to like 100 million parameters or something like this. So yeah, basically this seems to work all across the scale depending on your particular use case. Yeah, one other interesting thing to talk about very briefly is that, yeah, so obviously we submitted this to iClear. At iClear, you get very rigorous reviews, which is great. Somebody very fairly raised the concern that we trained on LibriLight, which is an English-only data set, model's quite big. Maybe we were just overfitted on English. So in order to address this, we basically tried evaluating the model on multilingual Libri speech, which has, I think, 6, 7 languages in. And yeah, we showed that actually there didn't seem to be too much overfitting, at least in this respect. So we could reproduce at least the languages that are present in multilingual Libri speech, which is admittedly mainly European languages. We could reproduce them pretty well, basically with a similar level of quality, even compared to some of the models which are trained on multilingual data sets. I think I won't play these examples just because we're really struggling for time now. But you can listen to them on the website and make up your own minds there.
Der Republikanism ist das Staatsprinzip der Aussonderung.
I don't know why that did that then. I clearly clicked in the wrong place, but that's a preview of what you can hear if you go to the website. So yeah, after the submission and acceptance of this paper, we did a little bit more work actually. So it had been the intention from the start of this work to actually put the weights for this trained model out into the world for people to use, and I mean mainly as a baseline for further codec research, but also so that people could try and build downstream applications from it if they wanted to. And in our initial tests, so yeah, we wanted to test like the most common downstream task, which is obviously TTS, right, for a model like this. And in our initial tests, we actually found that like basically the version of the model in the paper was difficult to model. So the LM, if you try and model that using a typical LM approach, you could get there, but there would be a fairly high word error rate. You would get substitutions sometimes. Basically, it seemed to be difficult for the LM to model. We looked around in the literature a little bit, and there seemed to be some precedents for this in terms of FSQ. So maybe this is where our decision to go with novelty bit us in the ass a little bit. So yeah, we chose this fancy new bottleneck. Turns out later work shows that it's maybe not the best for language modeling, but it is what it is. So before putting this out to the world, we decided we wanted to basically do something to try and mitigate this a little bit. And we did this by doing a further fine-tuning of the model. So we did force-aligned phoneme tagging basically between, I think it was the English portion of multilingual Libri speech. So we basically had, tagging of all the phonemes, time aligned with the audio. And then we did a regression on the bottleneck latents using a CTC head to make sure that the latents were always able to basically reconstruct these phonemes during the training time. Yeah, and this seemed to work quite well. So I'm sad that we couldn't put this in the paper because I haven't seen so many people using this approach. You can't add a load of new information to an iClear paper after it's been accepted, so we couldn't include it. But maybe we'll publish it somewhere else later. But yeah, we did this for the public model. Worked pretty well. It basically turns the TTS use case from borderline unusable to pretty good, at the cost of slightly damaging reconstruction metrics. Actually, talking to people who've used the model, now it's out in the wild, there's also maybe a question that it slightly damages the generalization as well. So when you do this, essentially like some kind of semantic alignment for English speech, it doesn't generalize quite so well to other languages anymore. I guess that's not surprising, right? That's something that you might expect. Yeah, so basically in the end, we released two versions of the model. So the version with the CTC fine-tuning that's probably the best for downstream English tasks, and then a version that doesn't have that for other experiments, basically. And they're both available on Hugging Face if you want to mess around with them. Yeah, and just a final quick couple of thoughts before we go to the questions. So some things that we learned through this process. I'd say the first big thing that we learned was that directly passing a real world signal into a transformer can potentially present difficulties. I guess this isn't surprising, right? So it's a very different kind of use of such a network compared to something where you have trainable embeddings like an LLM. Yeah, we also learned that you've got to be careful if you're scaling your decoder too much, this can produce potentially problems and reveal issues in your loss functions. Yeah, what do we want to do in the future? We want to adapt this architecture to work better with music. Yeah, obviously that's already ongoing. That's my that's my big interest. So watch this space for new results in that direction in the future. Yeah, also, we're obviously very interested in how we can eliminate the last elements of convolution in this architecture. I think this is if you've been keeping up with recent literature, especially in the image domain, it's actually quite obvious how you do this in the end. So I won't reveal it yet because that's going to be a paper soon. But like, yeah, you can do this and you can do it in quite a nice way, and everything looks even neater and more kind of simple once you do this. Yeah, and then, right, maybe some limitations or regrets about the approach we took. Yeah, so maybe in retrospect, using relatively small data sets and large parameter counts was not the best choice. It's possible, even though we showed pretty good generalization performance, that maybe to a certain extent the model is overfit. Maybe this even explains why it sounds so natural. Who knows? I think it's definitely the case that for future work with this architecture, it is needed for the data to be scaled up as well. Yeah, the other slight regret slash thought for the future is, okay, FSQ was really great. It allowed us to very specifically optimize for really good reconstruction per bit, but it seems to damage to a certain extent downstream use cases. So it's kind of a little bit of a poison chalice for us. So it did allow us to produce a good paper, but is it a practical model to use for other things later? Maybe it damaged that a little bit. So who knows if we would use that again in the future? Maybe RVQ is more practical. Yeah, and that's it. Sorry, I was a bit too slow, but we do have 5 minutes for questions or so. I'm super interested to hear all your thoughts about this. How do we do you want to choose questions, Bruna, or shall I
Uh,
just go through them in the chat?
I'll just ask them.
Okay.
Yeah. Thank you for the talk. So someone asked regarding the input-output representation. Why wasn't it an option to use critically sampled linear spectrograms without overlap and a rectangular window? This would certainly introduce heavy spectral leakage, but the transformer could well learn to produce spectral frames with
Yeah.
rectangular.
So absolutely correct. We could have done. I mean, I kind of alluded to that a little bit. So in the end, the reason that we didn't take that approach was basically the same reason that we didn't use MDCT or wavelet filter banks. So we found that basically the error that you got from reconstructing a non-perfect spectrogram that was without windowing and without overlap was more irritating. So you would get these typical. I feel like we're pretty attuned to recognizing spectral artifacts because we recognize them from MP3 and things like this. So it just didn't sound as good to us, basically. So not super scientific, but yeah, that was the reasoning. You raised your hand, Una.
Yeah, basically, thanks again for the talks. I have a couple of questions. The first one is you mentioned that you managed to make FSQ like RVQ, like you have a residual FSQs. Could you clarify
Yeah.
a little bit on that? Is it like multi-scale? Because I have seen that you have like three different range of values. Like how it works. Like first you start from a larger values, then go over, or because what I have
So
seen in the literature, the FSQ mostly work with group vector quantizer. So they split the embeddings. So I wonder how it works in your case.
So in our case, it's actually fairly simple. I should have drawn a graphic for this. Basically, it just arises from um, it's because of the equal spacing of the quantization levels in the FSQ in the projected FSQ domain, right? So because they're predictable, you can work out how to hit those same points from the bigger code book by superimposing multiple stages of a smaller code book, essentially. It's really hard for me this would be really easy to explain if I had a blackboard, but
I
I
see.
should have drawn a diagram. You can actually see it quite easily. Like if you draw out the levels, for example, if you draw out the 9 levels and then draw out the way that you would decompose this into 3 levels, the scaling, then you can see quite quickly how it lines up. We
I
don't have
see.
a mathematical a real strong mathematical justification for this decomposition yet. That's something that we'd like to do in the future, but intuitively, it makes a lot of sense when you look at it kind of graphically, and in practice, it basically works with, like, we empirically we tried this for many different combinations, and it works essentially perfectly. So yeah.
I see, I see. And one more question is like, you have this extra step that you fine tune this BabelM output.
Yeah.
So I wonder why you not train the encodec in the first place with this extra loss, like what they have done in Mimi or a speech tokenizer. Why you decide to have an extra step for that?
Well, so what they do in Mimi and speech tokenizer is a little bit different, at least as far as I remember. So correct me if I'm wrong. So in their cases, they're doing distillation on the bottleneck latents.
Yeah.
So we weren't doing that. So we're actually applying this perceptual loss to the reconstructed audio. So it's actually doing a completely different thing, potentially. So it's not enforcing that there's certain semantics in the bottleneck. It's enforcing that you can think of it as a different kind of spectral loss in a way, right? So what WAV-LM is doing in the end is taking a spectral representation of the signal and then processing it through a bunch of layers. So you can see it as a really complicated, like, projection of the spectrum that's focused on particular aspects of the audio that are relevant for the semantics. So yeah, we're applying it on the end. So it's doing a different thing. It's more directly affecting the audio quality rather than affecting the semantics of the latents. In terms of why did we do it as an extra step, that's just a function of deadlines. So yeah, we were doing our big model runs. Yeah, we didn't have time to train it from scratch again with that loss added. We wanted to try it as a fine tune, and then it worked as a fine tune. We have tried it from scratch with the WAV-LM loss as well. That does work fine. But yeah, so what we reported in the paper is the truthful representation of how we did it, which is do it a bit without the loss, then add the loss and continue, as these things often go.
Maybe my final question is that I have seen that you use non-causal sliding windows, so it makes your model non-streamable. Have you tried the streaming version of your model to see how it works in a streaming fashion?
Yeah, sure. Actually, there's results for that in the paper. So that's a relatively simple adaptation. All you have to do is adapt the sliding window to be causal, and then you replace those few convolutions that are still there with streaming or causal ones. Yeah, and actually, so we tried this as a fine tune of the final model, and it works fine. There's a very slight quality degradation, but basically it's good. So I think the reason we didn't concentrate on that more, and we actually didn't release that causal version of the model is simply that the rest of the design decisions around the model, for example, like the size, they don't really support the streaming use case. I mean, it might work in that context, but it didn't seem like if we were building a streaming model, we would have done it differently. So we didn't want to put out like a compromised streaming model just because we could. We'd rather just leave it in its non-causal version, pure to its original goals. And then, yeah, maybe us or someone else is going to do a causal version that's like designed specifically for that streaming use case in the future.
I see. Thank you. Then we have one more question in the chat, I guess.
Yeah, exactly. That's what I was going to say.
Yeah. If you could explain how the objective metrics work for speech quality, and are they well aligned with subjective tests?
So my opinion is no. This is a constant problem for this work for us on the speech side, but also, to be honest, on the music and general audio side. Like the objective metrics don't align super well with perceptual quality usually. I mean, I think this is why this is actually a really active area of research, right? There's plenty of people working on trying to come up with all kinds of different variations on models that can estimate subjective quality. I think that's a super exciting area of research, like specifically for this reason. I mean, there are things. So, I mean, PESC gets you a little bit of the way there, but I think it's not great, to be honest. UTMOS seems to be quite good, and our model actually does quite well by UTMOS usually. We didn't have it in the paper, but other people have evaluated it in other papers, and we're usually doing really well there. So that seems to correlate well with our subjective tests at least. But the basic metrics like SISDR, things like this, actually especially SISDR, I think this is a long, long way away from something that describes the perceptual quality. It really just, in fact, it can often be misleading, right? So you can have a pretty generative codec that perceptually sounds really good, but has terrible SISDR, and that becomes kind of useless. So, yeah, that feels like a really big problem in the area to me, and one that I'm glad that people are working hard on addressing. Cool. Do we have any final questions, or are we done?
Okay, perfect. Thanks a lot. It is a really great presentation, lots of details. That is like very essential for designing the models. Thank you for sharing.
Yeah, you're welcome.
Thank you everyone for joining the reading group. Next week, we have Jayo B from Telecom Paris. He's going to talk about one of his recent paper, learning source disentanglement in neural audio codec. Hope to see you all next week.
Thanks, everyone.
Thank you.